Hello everyone, I'm Maria Georgousi. I'm a physics master student at 4th in Greece, in Crete, and today we'll be presenting the submitted work, Gravitational Waves from Double White Dwarfs as Probes of the Milky Way. First of all, I would like to thank my colleagues in this project, Valeria Corol, Mauro Pieroni, and my thesis supervisors, Nikolaos Karnesis and Nikolaos Terioulas. For anyone interested, you can always look up our preprint in archive with this number. So let's start. What is the basic idea of this project? Actually, what we wanted to do is investigate somehow the confusion foreground signal so that we can actually build a framework, and using this then to probe and to analyze, to study several Milky Way properties. How are we going to do this? We need some kind of sources. LISA isn't launched yet, but we don't care because we have simulations, and so we can actually make our own data, our catalogs and our models. You all know that LISA is going to detect a great variety of different sources, but in this project, we are going to study the most common one, the most common type, which is the double white dwarfs. And it is estimated that it is the number is around 10 to the 4, the population. So it's quite good because we're going to have a good signal. But again, all the other types are going to create a soup of signal, let's say, a foreground confusion signal, as we call it, which will exist under a few, in less than a few millihertz. And this signal is going to change a little bit the main LISA signal. So we're trying to see what happens with this. Okay, so we have our sources. Then we need to actually build catalogs that are going to help us to analyze and to study whatever it is that we want to study, the foreground signal. So for our main population, our main catalogs, we used the Monte Carlo technique to generate them. And also for the initial mass function, we used the model of Krupa et al. The SIBA code was used for the binary evolution. And again, we used two different models for common envelope parameterization. And how are we going to proceed? In order to estimate this signal, we used different methods and tools such as Bayesian statistics, Markov chain Monte Carlo methods, and certain SNR criteria. For example, we consider that every source that has a signal to noise ratio more than 5 is going to be considered resolvable, let's say, and does not take part in this confusion signal. Here, there's an example of some data, where data we mean the main signal with the noise, of course, and you can see here the axes are the power of spectral density over the frequency. Actually, these two graphs are the same. Basically, the right one is the rescaled left one. So what are the properties that we studied? First of all, the shape of the galactic disk. We considered 3 catalogs with different disk scale heights. Z, which means that Z is either 100, 300, or 500 parsec. And we got these results. As you can see, in both of the graphs, the differences are minor. We can barely distinguish the 3 catalogs. And what does this mean? Actually, that there's no significant effect. If we change the geometry of the galactic disk, then we don't actually detect a very different signal with LISA. Also, I've included here the histograms of the extracted sources for the 3 catalogs respectively. Moving on to the second part of our analysis, we wanted to see what happens with a stellar galactic mass. Here we had a main catalog denoted as N100, and then using some methods, we extracted a certain ratio of the mass. So we had another 5 catalogs denoted with N50, for example, means that we had the 50% of the mass of the initial catalog, and so on. So here again, these results show us that now we have actually differences in the signal that we get. So it's not the same as in the previous case. We actually get something here. Moving on, we try to develop a global fit and a new model. That model has four equations with four basic parameters. Our parameters are, as you can see, alpha, Fn, F1, and F2. And these are the graphs that show the variation of the parameters over the mass. So this is actually something new for us. We think that this is quite nice and important because if we succeed in taking the LISA data and fitting the model on them and then somehow find the values of these parameters, then we can somehow estimate the mass of the galactic of our galaxy using a new method, gravitational waves. And last but not least, we try to study three astrophysical priors, this time not based on the foreground signal, but on the resolved sources. And as you can see here, the priors are the main frequency in the first graph, the time of coalescence in the second one, and the chirp mass in the third one. For more details, because our analysis was quite complicated, I suggest that you refer to our paper for more details. And to this point, I would like to thank you for your attention.